So far, quantum mechanics seems pretty weird, hey? Niels Bohr, responsible for the planetary model of the hydrogen atom, once said, "Anyone who is not shocked by quantum theory has not understood it." While that may be the case, another famous physicist, Richard Feynman, once said, "I think I can safely say that nobody understands quantum mechanics." Now, Feynman didn't mean that quantum mechanics is a useless theory, but that the quantum world behaves so strangely compared to our macroscopic world that our human intuitions cannot be relied upon to predict what will happen. Quantum tunneling is just one such example of how strange quantum mechanics can be. How can tiny particles vanish on one side of a wall only to appear on the other side? Well, if we recall from our last lesson, we don't know exactly where particles are as a result of the uncertainty principle. If we don't know exactly where something is, how could a wall know either? That's the basic principle behind quantum tunneling, that indeterminacy, or uncertainty, can lead to a whole host of outcomes. But quantum tunneling is related to a process within black holes called Hawking radiation, so we need to understand that in order to continue. As we saw previously, one of the fundamental relations of quantum mechanics is the Heisenberg uncertainty principle. In a practical sense, it states that no matter how accurate our instrumentation, the experiments we conduct will always be limited in the accuracy of their results by at least h bar divided by 2. But it's not just our instruments, the entire universe obeys this uncertainty principle. The uncertainty principle has an important implication when we think about the vacuum. Normally you'd think of the vacuum as a void, space that is completely devoid of material, matter, and energy of any kind. In the context of quantum mechanics, that simply cannot be true, because if there is absolutely nothing, that would imply certainty. Certainty about the fact that there is no energy or mass in the vacuum. If you are certain that there is no energy in the vacuum, then you are saying that the uncertainty in the energy, delta E, is 0. However, the energy-time version of the Heisenberg uncertainty principle states that delta E times delta T is greater than or equal to h bar divided by 2. In essence, you can never be totally certain that you have a true vacuum, since delta E has to be larger than 0. The uncertainty principle tells us that what we think is a vacuum actually has, for brief moments of time delta T, particles appearing and disappearing. This quantum view of the vacuum is sometimes called the quantum foam. In general, the uncertainty principle is meaningless in everyday life. We never measure things so precisely that we would run into such a limit. But what if instead we zoomed down into the quantum world? What do you suspect we'd see? Let's shrink down in spatial dimensions to about the size of an atom, and in the time dimensions so that we're living through nanoseconds as if they were seconds. Already you can see that space-time itself is strange at the quantum scale. Scientists call this mess the quantum foam. This is an artist's illustration of the quantum foam, and as you can see, the foam appears to be frothing with activity. What's going on down here? Since we've shrunk ourselves down in space and in time, we're living in the cold reality of what the uncertainty principle enforces on the universe. For lack of a better term, uncertainty. Down here, the foam can essentially be anything. A proton-antiproton pair here, an electron-muon-neutrino entanglement there. The quantum foam might even generate tiny wormholes. As long as these species last for only a short time, they can have lots of energy. Physicists call particles born of the quantum foam virtual particles because, for all intents and purposes, they exist for such a short period of time that we in the classical world barely measure their existence. We can borrow energy from the universe as long as we pay it back very quickly. So now a question we might ask is, what happens if we put a black hole nearby and zoom in on the quantum world at the boundary of the event horizon? Do virtual particles get pulled across the event horizon? Classically, we'd say no. For one, the quantum foam is not a result of classical theories like general relativity, but given its existence anyway, we generally think that virtual particles don't last long enough to fall in. However, we also have to consider where a particle is, because in this universe, we obey the laws of quantum mechanics. So here we are, among virtual particles in the quantum foam, and this black region is the event horizon of our black hole. Let's see if we can pin down an electron and its antiparticle, the positron, when they emerge from the quantum foam. This particle pair is called positronium, because it exists, albeit temporarily, as a quasi-atom, until the universe decides its time is up, and it vanishes back into the quantum foam. But the diagram here doesn't show a complete picture, because the electron and positron in the image have definite positions. If we were to truly draw this properly, each would have a much larger probability density, which is to say, regions within which the particles are likely to exist. Probability densities, characterized by something called the wave function, are places where there are probably particles. So for our example positronium, there's a 100% chance that we'd find them inside this boundary. But look, the way we've drawn this, there's a good chance that we could find the blue particle, not just on the boundary of the event horizon, but within it entirely. That's a bit goofy, you might think. The particle-antiparticle pair have come into existence, and before they could repay their energy to the universe, one of them vanished into the black hole. So now we're in a pickle. We needed that blue particle to annihilate the red one, but instead, now we just have a red one left with no companion, and it doesn't want to stick around. Essentially what you've just witnessed is Hawking radiation, the process by which particles can kind of escape from a black hole. When a particle-antiparticle pair pop out of the quantum foam right on the boundary of a black hole, the outgoing particle actually steals energy from the black hole system. It doesn't have to pay the universe back for that energy, instead the black hole had to pay for that part of the equation. Not only does that mean that particles appear to come from the event horizon, but also that quantum mechanics allows black holes to evaporate slowly. So it's pretty obvious that quantum mechanics can do some pretty strange stuff. They can whittle away at a massive black hole until nothing remains. In the next lessons, we'll develop a further understanding of this concept by examining a black hole's temperature, its entropy, and eventually we'll determine how long a black hole has to live in the face of quantum mechanics.